Right, good afternoon, everyone. I guess I should make a start. This is BGP Techniques for Internet Service Providers tutorial. For those of you who've been to NANOGs before, I tend to give a tutorial on BGP, or at least one particular aspect of BGP for the Sunday afternoon tutorial sessions. So this time, this is the techniques for service providers. Given the 2 hours that I've got to talk here, I'm not going to go into the absolute basics of what BGP is, so I'm going to miss out the first section that I would probably normally cover. And I'm going to look more at some of the scaling aspects, some of the operational parts and so forth that generally forms the latter part of the techniques tutorial. Now this assumes that you have some basic knowledge of BGP. It's not that, it's not aimed at a BGP expert, I would say. If you're a BGP expert, you probably could do this a lot better than I could. So what we're going to try and do is just look at some of the bits that take you away from really the first steps of getting BGP configured on your network, and then how you go about trying to implement it and scale it as your own network grows. My name is Philip Smith, work for Cisco. I spend most of my time traveling around the world. So I was just saying, just before we started, I've just come from the RIPE meeting in Stockholm. I was at AFNOG in Mozambique before this, at the African Network Operations meeting. So I generally spend most of my time working with internet service providers around the world. So what you'll find in these presentations, a lot of my experiences that I've seen in many parts of the world, not just in North America. So the presentation slides, they're on the NANOG website, I hope. At least I hope that Susan Harris has put them up there by now. If not, you can also get them at the FTP site that I've put up on the screen. Basically, it's ftpeng.cisco.com/pfs/seminars. And if you look for the NANOG 34 presentation, you will have found it. There are also lots of other materials there on BGP, whether you want interested in multi-homing or troubleshooting or various other presentations based on this. You're welcome to whatever is of interest to you there. There's a fair collection of materials there. Also, feel free to ask questions during the presentation. You don't have to wait until the end, even though I seem to find that most people want to wait to the end, but feel free to ask questions anytime during the tutorial. If you do want to ask a question, can you please use the microphone, because the session is being recorded. And when you do use the microphone, if you say your name and affiliation or who you work for or whatever, that will be useful as well. So, what we're going to talk about? Well, for the 4 topics, we're going to fly very quickly through the BGP basics. As I say, there's not time to cover the real starter part of it. I want to spend more time covering the BGP scaling, using communities within BGP, and how you go about deploying BGP within an ISP network. So just a quick recap of the basics. BGP, it's a routing protocol used to exchange routing information between networks, so between service provider networks. It's what's called an exterior gateway protocol. So it's a protocol that basically runs between exterior gateways or exterior facing routers on your network. There's an RFC that, way back described BGP, RFC 1771. I think most people recognize these days that that RFC is completely out of date. And in fact, there's been a lot of work in progress over the last few years in the IDR working group in the ITF to bring this up to date. The last version of the draft, and I think it's sitting with the ISG at the moment, is the draft I've listed there, the BGP 4-26. I believe that's going to become an RFC real soon, like within the next month or so. BGP relies on having an autonomous system number. That's its fundamental operating thing. So BGP does not really care about your routers or your network design and so forth. All it really cares about is this autonomous system concept. BGP passes routing information between autonomous systems. So the autonomous system is a collection of networks with the same routing policy. So generally, an ISP who is running BGP will be running it within an autonomous system. You generally find that one autonomous system is equivalent to one ISP network. You may find that some ISPs will split the networks into different autonomous systems. Within that autonomous system, you have a single routing protocol. There's usually single ownership, single trust, single administrative control within this autonomous system. I say usually, it doesn't always happen, but it's pretty hard to try and run one network within an autonomous system if there's several owners or managers of that network. And the autonomous system is identified by a number. It's a unique number. So like an IPv4 address, an autonomous system number has to be unique on the internet. It's a 16-bit integer. There's 64,500 of them available for public internet use, and another 1,023 which are kept for private use. And the first and the last AS number are reserved for no particular use. 32-bit AS numbers are coming quite soon. We've got as far as about 38,000 in the assignments of autonomous system numbers to ISPs. So they are, well, the 16-bit space is running out reasonably fast. 32-bit ASs are coming soon, the internet draft is there, and one AS number in the 16-bit space is reserved for the transition. AS numbers are distributed by the regional internet registries. So we have the 5 RIRs, of course. ARIN will serve the North American region, as I'm sure you're all aware. You can also get AS numbers from the upstream ISPs who are members of one of the registries. So if you yourself are not a member of a regional registry, you can go to your upstream ISP or any other ISP and obtain an AS number from them. Current allocations are set up to 37,887. Of these, around half of them are visible on the internet. So where the other half has gone, of course, is the usual mystery and discussion that's been mentioned on various lists and public forums over the last few years. Current estimates are that 4-byte AS numbers will be required by around about July 2010. Some of you may know Jeff Houston, who's done a lot of analysis work on the V4 routing table as well as AS numbers. His latest projection at the current growth rate that we're seeing, at least the allocation rate being made by the registries, it's going to be around about the middle of 2010 when the last 16-bit AS number will have been used up. So, what else? About applying policy with BGP, well, policies are applied to try and influence how BGP selects the paths through the network. BGP has attributes. These attributes can be manipulated to apply policies. And policies generally mean determining which prefixes are blocked, which prefixes are announced. In other words, what you're going to send to your neighboring ISP, what you're going to hear from your neighboring ISP, and so forth. You can also use policies to try and determine which AS paths are preferred or permitted or denied within BGP, and also to determine route groupings and the effects that those particular route groupings are going to have. So that's basically how a lot of the connectivity will work in the internet. You can set up BGP by itself just for each external-facing router to speak to every other external-facing router, but as the whole internet, or as the internet as a whole, this is not really going to work too well. Most ISPs have business relationships with each other, and the way they implement these business relationships is by using these policies, the policy language within BGP. The major decisions are generally made on prefix, so what address space that you're going to announce or your neighbor is announcing, depends on the AS path. In other words, the list of autonomous systems that the prefix has gone through the internet to get to you, and also the actual community membership. As I say, I'm not covering what these basic attributes are, so hopefully you know what these are. The tools, most implementations, I say, I'm not going to go into any specific configuration examples, keeping this generic, but you find that most implementations of BGP from whichever vendor will have tools to apply policies within BGP. So these are manipulating prefixes, mostly by filtering. They've got AS path manipulation and filtering. So AS path manipulation can be doing AS path prepending to make your path look longer than it would otherwise be, or for filtering, in other words, excluding particular AS paths if you don't want traffic to go through certain destinations. And you can also play around with communities, community attributes, and so forth, which I'll show you a little bit later on in the presentation, some examples of that. Again, the implementations will have policy languages, some of varying power, which can do various match and set constructs to try and implement the policies so that you've got particular routes chosen through the network. BGP started off in the early days with being a fairly simple inter-domain routing protocol, but as people came along wanting to add things to it, there was a requirement for what's called BGP capabilities. In other words, when you brought up a peering session with a neighbor, your router could negotiate with the neighbor what new features of BGP it could support. The way that BGP was extended to do this was adding this capability functionality, and that was documented in RFC 2842. The capabilities parameters are passed in the actual BGP open message. So when you start a BGP on your router, it sends an open, basically a hello to the neighbor, and in that open message it will indicate what it actually supports. And of course, if your neighboring router can support that capability, then you have the negotiation happening like that. Unknown or unsupported capabilities result in the notification message. There are various capability codes. The first 64 are assigned by the ANA, by the IETF consensus method. The next 64 are assigned by ANA on the first come, first served basis. So they're generally, if individuals want to use a capability for some particular thing, they apply to the IANA and they get their number. And the final 128 are vendor specific. So you tend to find if a vendor wants to implement a new feature in BGP that they'll use one of the codes 128 and above. Current capabilities that, well, I know about and that are documented on the IANA website there. Well, capability number one, multi-protocol extensions for BGP. That was actually the reason the capability codes were developed. BGP did just unicast IPv4, but then we wanted to try and do multicast for BGP, so that was multicast IPv4. And then IPv6 came along, and so forth. So the multi-protocol functionality was added into BGP, and the way that you found out whether your neighbor could handle multi-protocol BGP was chat on the BGP capability number one. Route refresh, which I'm going to talk about a little bit, that's a very important capability, that's number two. Cooperative route filtering, that's still internet draft state. Multiple routes to destination capability, well, that's an RFC, I don't really know any implementation yet. And then, of course, the next four is still work in progress. So the multi-protocol extensions, as I was saying, it's quite a whole different world here. It lets BGP support more than v4 unicast routes. So, for example, the v4 multicast, v6, v6 multicast, VPNs, and so on. I'm not going to cover any of that. I mean, as I say, these can be a whole new tutorial on the different multi-protocol support that BGP has. Route refresh, we'll cover in a bit. The other capabilities are still in development. So that's the way that BGP will extend. So if you need to do new or more wonderful things within BGP, you'll find that it'll all be set up within the capability negotiation there. Now, that was really the basics that I want to try and cover. Rest of the tutorial is really going to all be about scaling and operational parts for BGP. So the first bit is scaling. I'll have a look at three of the really important scaling techniques that are basically requirements for service provider networks. The main issues are, how do you scale the iBGP mesh beyond a few peers? As I'm sure you're all aware, at internal BGP, each router must speak to every other router in the network. This is because an iBGP speaker only takes prefixes it hears from an external peer or prefixes that is generated locally and passes them to another iBGP speaker. It won't take any prefix that is learned from another iBGP speaking router and pass it onwards. I mean, this is always a major gotcha. I mean, I do lots of workshops all around the world, and when I'm teaching people iBGP and they're setting up the first iBGP mesh in the classroom, they set it up like they would set up an internal routing protocol. And people always end up sitting, well, why can't I get this prefix from here, and what's happening, what's going on there? They don't realize this requirement for iBGP to be fully meshed. So that's a fairly important one that catches people out. I also find a lot of the troubleshooting parts that I do is that people don't remember to do the full mesh. They may add a router but forget to set up the iBGP sessions with the 20 other routers that they have on the network. And then, of course, the issue comes, what happens when they have 50 routers in the network? What do? You're maintaining 49 iBGP sessions on each router with every other one, and that doesn't really scale. The number of routers goes up, the number of iBGP sessions goes up. The second one was also very important. I guess these days it's less of an issue because, well, it's all been part of the router for so long now. I started in the internet industry probably about 1992 doing this, and well, implementing new policies was actually a pretty major issue for us. You couldn't do it. The only way to implement policy within BGP was to do a hard reset of the BGP session. And you know what a hard reset does on the internet these days. It cuts you off for however long. And of course, the other one is keeping the network stable, scalable, as well as simple. Well, stability, I think, is the major point. Okay, route refresh. Well, BGP peer reset is required after every policy change. Right? If you're talking iBGP or eBGP to your neighboring router, you're filtering some of the prefixes you've got from that neighboring router. Well, those prefixes are discarded. Okay? If you decide to throw all the prefixes away originated by a particular AS number, right? They are thrown away. Your router doesn't keep any record of that. If you now change your policy to say, oh, well, I want to hear these prefixes, you can certainly change the inbound filter, which will then let the prefixes come in. But because you've got no record of what you've thrown away, all that will happen when you apply the new policy is you'll only get the updates. You won't actually get the routing table as you expected it. So what you have to do is you've got to tell the BGP speaker to reset the session. In other words, tell the neighbor to resend you all its announcements. Now, in the old days, as I was saying before, the only way we could do this was with a hard BGP peer reset. There was no signaling mechanism between your router and your neighboring AS's router to say, hello, can you just send me the full routing table again? There wasn't any way of doing that. And the way was to shut down the BGP session. Of course, terminating the BGP session means you lose connectivity to that particular peer. Your prefix is no longer announced to the internet, so you disappear from the internet. You lose all other access to the internet as well. Basically, it was pretty terminal. As I say, it's an understatement there. Severely disrupts connectivity for all networks. I mean, it knocked you out for a few minutes. So to solve that particular issue, as the commercial internet was growing, route refresh was basically invented or introduced to BGP. I mean, some people call it soft BGP peer reset. The official name is the route refresh, where the BGP peering remains active, but what you do is you send a notification to your neighbor to ask them to send you the complete update or complete routing table again. And this route refresh only impacts the prefixes affected by the policy change. Okay? So all your customers who are using your network and so on, everything will carry on as normal. Forwarding is not impacted, nothing changes. Only change that will happen is, say you were denying prefixes before, they're now allowed in through the update by the route refresh. Those prefixes will now be added to your routing table and you get connectivity that way. So the capability, it allows a non-disruptive policy change. For most implementations, you don't need to configure it. In fact, for many implementations, it's now just the default. It's what happens. It's automatically negotiated at the peer establishments. You don't need to add any special configuration usually. Doesn't require any extra memory on the router. As I say, it's just a little signaling mechanism between your router and your neighboring router. But it does require the peering routers to support RFC 2918, the route refresh capability. Now, I've had this slide for several years. I'm actually not aware of any implementation that doesn't support 2918. I think virtually all of them that I know that do. I've access to quite a lot of routers in many different places, and virtually every one that I'm aware of now supports route refresh these days. So, as I say, you can still find out whether a neighbor will support it or not, usually from just the status display of the BGP peering. Again, the implementations I know, if you don't support route refresh, or if your neighbor doesn't support it, I should say, they will have some workaround that will let you do this soft reconfiguration without actually tearing down the BGP session. Okay. Workarounds tend to be the router, you can configure the router to store all the updates that have come in before any policy has been applied. Okay, that's default on some implementations as well, where actually all the updates before policy is applied is stored. So if you need to apply any change to the policy, you can do it without having to reset the BGP session. And as I say, only do a hard reset as a last resort. If you consider it the same way as a hard reboot, sorry, as a router reboot, treat it the same way as that. So you would only reboot a router during a maintenance period. You'd do that only when the network is running really, really quietly, probably like 4 o'clock in the morning or something like that. So that's the sort of time you do a hard reset of the BGP session. The rest of the time, using the route refresh capability is the recommended way. So the next one, flap damping. A route flap is basically the going up and down of a path or a change in a BGP attribute. So a BGP withdraw followed by an update is generally treated as a flap. If your physically connected eBGP neighbor goes down, that's not treated as a flap. It's just if you hear a BGP withdraw message followed by a BGP update message. The withdrawal is caused by a prefix disappearing. The update is caused by the prefix being re-announced. If you hear that, that is a flap. Now, a route flap will ripple through the entire internet. If you withdraw a prefix, it basically means you send a withdraw message to your neighbor will send a withdraw message to their neighbor, and so on, and it propagates through the internet. Causes instability, it wastes CPU. Now, these days, I suppose route flaps are just one of these things that happen. Routers these days all have RISC-based CPUs. They're all pretty fast. Back in the 90s, route flap damping was actually a pretty serious issue. Motorola-based CPUs, they were very, very slow or relatively slow to what they were trying to handle, and route flaps caused a fair amount of issues. The other problem back in those days was that dial-up connections to the internet were still very popular. These days, people who tend to dial up tend to be a home user on a single PC or somebody on a laptop traveling around. 10 years ago, it might have been entire networks would dial up. They would have the router, analog modem dialing up to the ISP. When they dialed into the ISP, their /24 address block was announced to the internet. And there was a lot of this happening back then. It was not uncommon to see several hundred announcements or withdrawals of such prefixes every minute. And it was actually a serious issue because the routers are spending a lot of time, significant amount of CPU, probably 20–30% in my experience, just spending CPU handling these withdrawals and updates. Okay? And that's where the flap damping requirement came in. Because people said, well, somebody's dialing in. They dial in for 2 minutes to get their email, then they hang up. 2 minutes later, dial in demand kicks in again, dial in, get email, hang up. And you're seeing this oscillating back and forth every 3, 4, 5 minutes, which was getting pretty painful for a lot of ISPs. The aim of damping was to reduce the scope of route flap propagation. So these prefixes were going up and down in a regular cycle. You just didn't want to bother with those. Whereas what you want to try and do if somebody's announcing a new address block, or maybe they had a break in their network which took them down for half an hour or a day or something, you would treat that normally. Requirements then were fast convergence for normal route changes. Okay, so the normal announcement, you want fast convergence for that. So you don't want to change BGP like this. You want to use history to try and predict the future. So if a prefix is flapping a lot, you want to, well, you could basically say it's going to carry on flapping a lot. Whereas a prefix has been very stable, it's going to remain stable. So the idea is to try and suppress oscillating routes, but advertise the stable ones. RFC 2439 documents what, well, the whole theory and so forth are behind route flap damping, what's trying to do. Basic operation is quite simple. You want to add a penalty for each flap. You want to exponentially decay this penalty. So the bigger the penalty, the longer it will take to decay. The bigger the penalty is caused by more flaps. One thing to note, which I've highlighted in red, and it's appeared as red as well, is that a change in attribute is also penalized. In my experience, that's never really been that well documented. It's one of these small print things. But actually that point is really a very important one, as I'll show you in a couple of slides' time. When this penalty goes above a suppress limit, so you define a suppress limit, then you don't want to advertise the route to BGP peers. So you're setting a cutoff. When the penalty goes above this cutoff, then you want to implement flap damping. So you'll allow maybe 1 or 2 flaps, but after that, you want to cut off announcements. The penalty is decayed below a reuse limit again. You re-advertise the route to the BGP peers. So the picture would look something like this. I say a picture is worth 1,000 words. This one describes it quite nicely. So we've got 2 flaps there. That's all sitting under the suppress limit of 2,000. The third flap, though, takes it over the 2,000 limit. Time axis along the bottom. You see the network is announced for the first 2 times it flapped. The third time it flaps, the network is no longer announced. You see the prefix carries on flapping until somebody spots the problem. It's when the penalty has just gone over 4,000. You then have the exponential decay all the way back down until you've reached the reuse limit, and then the prefix is re-announced again. So you see what this was trying to do. It's prefixes that maybe flap once or twice, we won't touch. Prefixes that flap a lot of times, we're going to hit those and hit them hard. Notice that like 3 flaps there has caused the prefix to be suppressed for quite a long time. It's only applied to inbound announcements from eBGP peers. You don't really want to do flap damping within your iBGP. iBGP is inside your network, and you should be in control of running your internal network properly. If your internal network is flapping, you've got to figure out it's something else that's actually causing that. Also, it only applies to the path that's actually flapping. I mean, if a prefix along one path flaps, you don't want to suppress that prefix entirely. If you're multi-homed, for example, you could connect through one ISP and, of course, another ISP. If one path is bouncing up and down all the time, well, you prefer to fail over to using the path that is stable. So flap damping will do that for you. If one path is bouncing up and down all the time, it will become suppressed using the flap damping, and then you get the backup path. Flap damping can be controlled. Again, all the implementations let you control the half-life, the reuse limit, the suppress limit, and the maximum suppress time. So you can set any of these values to what you think is appropriate for your network. So they allow various policy control with the flap damping. Apart from those values that I was talking about, you can use variable damping. So you can apply different damping to different prefixes, or prefixes have been learned by different paths and so forth. So it's a pretty powerful configuration tool that you've got here. Now, 10 years ago, this was actually pretty important to achieve, but I think since the turn of the century, at least certainly since 2001, there's been quite a lot of discussion an analysis of what flap damping is actually doing to the network. And I think the first bullet there is pretty important. A lot of people, and they still do these days, they look up the configuration cookbooks or the templates that somebody said, and it says, oh, you should switch on BGP damping because it makes your network stable. Well, yeah, it might make your network stable, or it might make something stable. And it also could cause a lot of problems as well. So that's what I've highlighted in red there. Flap damping should only be implemented to address a specific network stability problem. Because flap damping can and it does make stability worse, depending on how you connect your upstream ISPs, how richly they are all connected. Several ISPs have seen this, certainly in the late 90s, and well, this particular paper, this study by Morley Mao and friends, Route Flap Damping Exacerbates Internet Routing Convergence. They do some pretty interesting analysis work showing that flap damping can actually make things a lot worse than you expect. If you bounce a prefix just once, you can end up being completely suppressed for a substantially long time. Okay, so this is what people have called flap amplification. So you've got to be kind of aware of this. The flap amplification is caused because BGP does searching through the different paths that it has. Now remember I said, beware the attribute change is also penalized. That's what's happening. Because if you flap a prefix, your neighboring AS will probably see that prefix from you and it will see it from somebody else. So your one flaps or disappears, the best path then goes to your neighboring AS for this particular prefix. And what happens is that AS will send an update message to their upstream saying, well, I'm still hearing the prefix, but the AS path has changed. And the upstream says, AS path changed, that's a flap, bang. Okay? And so on, this goes through the network. And you can get a nice, interesting topology where all these AS path changes mount up. Okay? AS path change in the upstream, that may tip over a flap, causing that path to be damped, causing the next one to become a chosen path. So as BGP does this searching through the different AS paths, it will start accumulating penalty values and suppress the prefix, even though it may have only flapped once at origin. And I thought it actually took a pretty special set of circumstances to make this happen, even after reading the Morley Mao paper. But having worked with several ISPs trying to get multi-homing solutions working, doing the traffic engineering, it's pretty easy to see. You can go to Looking Glass, you can announce a prefix, withdraw it, and then maybe 10 minutes later the Looking Glass says 10 flaps. And it's like, wow, I only announced and withdrew the prefix. What's actually going on here? So you've got to be aware of this. So if you have to implement flap damping, it's pretty necessary to understand the impact on the network. The first thing, vendor defaults are actually very, very severe. I mean, the Cisco defaults are basically allow you 2 flaps and then you're gone for almost an hour. Okay, that's the worst case. And that's not good. And the sad thing is there are a large number of ISPs who just switch on the Cisco defaults or the Juniper defaults or whatever because they've seen it in a template somewhere. And, well, they're not really a very good thing to do. Variable damping can bring benefits. So some people do flap damping for particular prefixes or prefix lengths. That can bring benefits. Transit provider flap damping will impact PASs more harshly due to the flap amplification. I participated or tried to lead a discussion at the RIPE meeting 2 weeks ago about flap damping, what we should do about it, and it was quite interesting. Either it was the morning after the social event the night before, or people weren't interested, but there wasn't much discussion. People were like, flap damping, well, we don't particularly care anymore. There's not the same issue these days as there was. So the recommendations for ISPs still stand. The RIPE 229 document, which says, hang about guys, the vendor defaults are too severe. We want to try and hit /24s pretty hard, but everything, well, 22s, 23s we want to be careful with, and everything else we can pretty much leave alone. But as I say, we're starting discussion on whether this RIPE 229 document should carry on, or we should just say, don't bother with flap damping anymore because there aren't really the issues that we see. And for all the connectivity I've had, all the networks that I see, the amount of flaps that I see on the internet today is not as large as the number of flaps I saw probably 10 years ago when this was a pretty serious issue. So, flap damping. That was. Now, route reflectors. Well, this is the third BGP scaling technique. As I was saying earlier, the iBGP mesh, well, the routers participating in that have to be fully meshed. So every iBGP speaking router has to speak to every other iBGP speaking router in your network. So we've got 13 routers, you've got 78 BGP sessions. In other words, there's a half n squared-ish issue. Now, there are two solutions to this. The first solution that actually appeared on the internet was the BGP Confederation. But what you did was you split your network up into lots of different autonomous systems and then grouped all these autonomous systems together inside one confederation. I mean, that was the quick and dirty fix that was done to rescue certain ISP's network, and it was the first one that appeared in any implementation. But within a few months, there was another solution called the route reflector. And the route reflector basically, I suppose in the simple summary, was it removed one of the requirements for iBGP, and that was that an iBGP speaker cannot take prefixes it hears from another iBGP speaker. The change was an iBGP speaker could now take prefixes it hears from another iBGP speaker and pass them onwards. And that was basically the route reflector. See, large networks, if you have 1,000 routers in your network, which is, well, not unusual, not too unusual these days, that's nearly 500,000 iBGP sessions. And it simply doesn't scale trying to maintain this. So the route reflector was the nice way forward. The way it works, as I just was saying, the prefix comes in, it gets external BGP announcements come into router B. B, of course, passes that to router A. That's standard iBGP behavior. Router A, by default, doesn't do anything with it. It says, oh yeah, I've heard it from router B, that's fine. Router B will also send that prefix to router C if it participates in the iBGP mesh. If you make router A a route reflector, then router A will take the prefix it's learned from B and pass it on to C. And because you've done that, you no longer need router B to send any announcements to router C. So you get away from that requirement of having to set up the full mesh system. Okay, that's the basic principle behind the route reflector. You take prefixes you learn from one iBGP speaker and pass them on to another iBGP speaker. When I'm doing workshops with this, people then ask me, well, why was this not even thought about at the start? And, well, it's one of the questions probably for the BGP developers way back then. I don't know. And I often, well, have this debate about whether people should just start off from the beginning, setting up their networks as a route reflector-based network rather than the full mesh. Because changing over from a full mesh to route reflector, while it is reasonably trivial, it still involves work to make it happen. So there's some rules that go with the route reflector. The route reflector will receives a path from clients and from non-clients. It will pick the best path, of course. Best path is from a client, then it will pass that to clients and to non-clients. The best path is from a non-client, it will reflect it to clients only. So it won't take a path from a non-client and send it to a non-client. So it maintains that normal iBGP behavior. But prefixes are coming from clients, it will pass on elsewhere. The clients can be fully meshed if you want, as I drew down at the side there. But it's quite rare for that to happen now. Most people don't mesh the clients. The clients only have a relationship with the route reflector. RFC 2796 describes the actual route reflector system. So your network would end up looking something like this. So rather than these 12 routers being connected by full mesh iBGP, you kind of have this hierarchy. You've got the core network, routers A, B, and C sitting in the middle, and then routers around the edge, the clients. And in its simplistic form, this pretty well imitates how ISP networks are set up, where your backbone would be the route reflectors, and each router within the POP, the aggregation routers and so forth, would tend to be the clients. So it's quite a nice layout. You divide the backbone into multiple clusters. As if you're using OSPF, for example, you divide the backbone into multiple areas. You have at least one route reflector and a few clients per cluster. It's a typical layout. The route reflectors need to be fully meshed because they talk the normal IBGP with each other. The clients in the cluster could be fully meshed, but they don't have to. And as I said before, it's pretty rare for people to do this. Don't touch your internal routing protocol. There's generally no need to do that. BGP is only there to pass routing information around your network. It doesn't care about the physical connectivity between routers. So you don't need to go and redesign your OSPF or your ISIs just because you're using a route reflector topology. There are two new BGP attributes were introduced. The originator ID, which carries the router ID of the originator of the route. And there's a cluster list, which is a little bit like the AS path, but the cluster list is basically a list of cluster IDs. In other words, the route reflectors that the prefix announcement has been passed through. So it's a little bit like the AS path. It's used there to try and stop or avoid loop detection and so forth within the IBGP. It's best to set the cluster ID from the router ID. Okay, and I've said here the router ID is formed from the loopback address, the address of the loopback interface on the router, something in the case of Cisco boxes. So the cluster ID is automatically set from the router ID. And because your loopbacks are numbered by unique IPv4 addresses, then your cluster IDs are unique. Some ISPs, however, set up their own assignment strategy. So they set aside address block and they use that to set up their own cluster ID. Cluster ID is just a number, but it needs to be unique per route reflector. Which is fine if they do that, but as with anything else, it needs to be well documented. I've seen many accidents happen where people have had clashing cluster IDs. And they're not that easy to actually troubleshoot. Now, the second thing, multiple route reflectors can be configured in the same cluster. And in fact, the early documentation of route reflectors said, well, you know, you need to have route reflector redundancy, and the way to do it is to put two route reflectors in the cluster. And well, that was then. These days, that's actually a really bad thing to do. Because all the route reflectors in the cluster have to have the same cluster ID. If they've got a different cluster ID, then, well, it's a different cluster. But what happened then was the ISPs went to the other extreme. They read that, oh, well, route reflectors way to scale IBGP. So they set up two route reflectors for the entire network. One on one side of the country, another on the other side of the country, and that gave them redundancy. And they would end up with really massive looping, routing problems, loops, black holes, and so forth. It was really nasty stuff. And because the cluster ID on the route reflector was exactly the same, and if you missed setting up the BGP mesh properly, you basically have prefixes missing from different clients, and lots of annoyed customers who couldn't reach different parts of the network. Now, a router may be a client of route reflectors in different clusters. There's nothing stopping a client belonging to two different clusters. Again, early advice was, oh, well, you can't really do that because then you get duplicate information and so forth. And I mean, for me, I didn't actually realize this was any issue. I mean, I used to run UNet UK's network, and we did all this from the start. We had two route reflectors, well, one route reflector per cluster, but two clusters per point of presence, and we basically overlaid the mesh. And we were doing this all the time. We were reading all this advice on the net that was saying, oh, this is the way to do it. And the way that I was doing it couldn't possibly work at all, but it was. And funnily enough, it's all turned around because people realized that with the looping problems and the disconnectivity problems that having two route reflectors with the same cluster ID is not a good way of handling it. So the way to do it, each client has got two route reflectors, and they're in two different clusters. You overlay the clusters. So the picture would look something like this. It's a bit messy with colors and so forth, but I hope you can see the general idea. You've got 3 points of presence in the network. You've got, well, basically 6 routers that make up the backbone. Black lines represent the full IBGP mesh. Cluster 1 is the green lines in POP 1, so first route reflector would speak to the 3 clients, and the other router in the core, the red lines would be the route reflector for the 3 clients also. So if one router fails, the other one then fails over. Question?
Just to verify, so it is required then that the BGP route reflectors have to be fully meshed?
The BGP route reflectors have to be fully meshed, yes, because they're normal IBGP speakers. Okay, the only special situation now is talking to the clients. And if you indicate on the route reflector that a particular router is a client, it will then take prefixes it hears from other IBGP speakers and pass it on to the client. Okay. So this is the typical way that ISPs will now actually set up a route reflector system within their network. So rather than a full mesh IBGP, rather than just setting up 2 route reflectors to serve the entire backbone, they would do 2 route reflectors per point of presence with an overlay cluster. And this works very, very well. There are many really, really large ISPs, especially in Asia, who have set up the networks like this, and it works well. Okay, where do you place the route reflectors? Well, the second really important rule, which so many people manage to ignore, is always follow the physical topology. If you've designed your IGP for your backbone well, then it should be very, very easy to implement a route reflector system on top of it. Because your backbone, whether you're using ISIS or OSPF, your backbone is a very well-defined part of the center of the network. And that will be all those routers, or at least a proportion of those routers would be the route reflectors. And all the aggregation routers around the edge would be your clients. But always following the physical topology, it basically means the relationship between the route reflector and the client. Try not to have the route reflector speaking to a client that goes through another router. There you will definitely end up with problems. I mean, you won't necessarily end up with problems, but it's a high likelihood that you could end up with problems. And I've seen enough of those to know that it can be a major issue. Try and have a physical connection between the route reflector and the client. Okay, so in the previous picture here, while in the middle of the network, the IBGP full mesh, I don't care what the physical topology looks like. The relationship in the route reflector to the actual clients in the POP, those red and green lines, I'd quite like to be physical connections. Now, whether that's an Ethernet connection or actual physical point-to-point connections. But rather have that, not have a connection, say, between the router on the right going through, the router on the right going to the router on the left through something that's not even part of the cluster. You can end up with some quite amazing looping problems. So, typical ISP network, as I was saying, the POP has got 2 core routers. The core routers are the route reflector for the POP, and the clients speak to the reflectors. You've got 2 overlaid clusters. That's the way to do it. And I think you'll find that most modern documentation, certainly from the vendors, will now say this. But there's still a lot of old stuff out there that talks about making sure the router ID is the same, and so the cluster ID is the same, and 2 route reflectors per cluster, and so forth. That's generally considered a bad way of doing things now. Okay, the core routers have a full meshed IBGP, and you can create further hierarchy if the core is too big. There's no problem with actually nesting route reflectors. So a client of one cluster can be a route reflector for another cluster. And I haven't seen too many people go too deep, but 3 layers isn't that uncommon. So you've got a core, maybe a distribution layer, and then an aggregation layer. So you can nest these quite nicely. You can configure 1 cluster pair at a time. So this is the migration strategy. You eliminate redundant IBGP sessions, and then, say, put a maximum of 1 route reflector per cluster. You can migrate your whole network if you want to pretty easily. I mean, I migrated 70 routers way back many, many years ago. With a colleague, we did that in 1 maintenance period in about 2 hours, and that was pretty easy to do. The These days, I wouldn't really recommend doing something like that. I mean, being young and foolish is one thing, but I think with the commercial network these days, it's probably a slightly bigger proposition. So pick on one part of the network first, pick your route reflector, get a redundant route reflector as well, and then set up the client relationships with the reflector. Once that's going, just strip out the redundant iBGP sessions and watch it, see how it goes. Let it run for a week until you're happy with it, then pick on the next section of the network. So you could be something like this. So routers E, F, and G are now part of the cluster, with D being the route reflector. So you've stripped out the iBGP sessions from A, B, and C towards routers E, F, and G. So the E, F, and G only speak to router D. It's pretty easy to do. So just a summary of the scaling techniques. Route refresh should be mandatory. Try and make sure, of whichever implementation you're using, that if you need to apply new policy to your BGP session, that you do so simply by using route refresh. In the Cisco case, unfortunately, you've got to put in an option for the BGP reset command to actually use route refresh. So it still pains me to see so many people doing a hard refresh for a BGP session when there's, given the dangers of doing so. Route flap damping. Well, I've changed my tune from saying you must do this to only do this if you really understand why. If you're going to get a benefit on your network for doing it, then do so. If you're a transit provider, if you're more to the center of the internet rather than sitting at the edge of the internet, think hard about doing it. I mean, if you're providing transit to maybe 2 or 3 different autonomous systems, it's probably not so much of an issue. But if you're a major transit provider, in other words, you've got hundreds of ASs all connecting to you or getting transit through you, think hard about doing flap damping. And actually, it might be a good idea not to do it. Route reflectors, that's probably the way to scale iBGP mesh. Yes, there's still a lot of ISPs out there using confederations. Which is better? Well, I don't know. I tend to prefer route reflectors because I find them really easy. I grew up with them, but then again, you can find somebody standing out there who's used confederation since day one, understands how they work, and they're really happy as well. So it's almost down to a religion. The thing is, if you're running a full iBGP mesh and you want to scale to go to the next step, it's really easy to move to a route reflector. Moving to a confederation is generally pretty painful. Now, let's take a quick look at using communities within BGP. So I suppose this is partly a scaling technique as well, not so much within the BGP configuration itself, but how you'd actually go about implementing your network and making it easier for you. So as I say, it's another ISP scaling technique. What communities will let you do is group prefixes into different classes. Many, many years ago, when ISPs wanted to offer different services or different level of service to different ISPs, they set up different autonomous system numbers. So with one AS number for this class of transit customer, with an AS number for that type of customer, AS number for, and so on, or for different services they want to offer. And that was generally quite unmanageable because one router can only really belong to one AS and so forth. So communities came along and made this a whole lot simpler. Each community means a different thing and has a different result in the ISP network. Community values are defined by you, the ISP. Okay, there are some well-known communities. There are 4 well-known communities. But otherwise, they're defined by you, the ISP. And how you define them is entirely up to you. I suppose a simple way of describing them is a signaling mechanism. It lets you send signals through your network to do particular things. They're generally set at the edge of the ISP network, so it can be set at the customer edge, where customers will connect to you. Customer prefixes can belong to different communities depending on the services they've purchased. Okay, I've got an example of this coming up. Or they can be set at the internet edge, so transit provider prefixes belong to different prefixes depending on the load sharing or traffic engineering or the demands from the BGP customers. So, simple example. How this would work at the customer edge. ISP's got 3 connections to the internet. So it goes to an internet exchange point. So that's for all the local peers. So you've got the local peers in your economy, your region, whatever. You've got that one. You've got private peering. You may be competing with another big ISP in your area, so you have a private peering with them. And you've got a transit provider or two who's providing you visibility to the entire internet. And so the service you can sell to customers is the option of purchasing any combination of the above connections. Okay, most people you'd think would just want to buy access to the whole internet. But as we found out, well, I certainly found out, this is not necessarily the case. Some people may only want connection to the internet exchange point peers. They may not want to use you for transit to the rest of the internet. So you can use communities to make this very, very easy. Let's say before communities came along, you should have seen the filter lists that we actually used. The filters were massive to try and handle all this, because we had customers who only wanted to go to the London Internet Exchange Point, with customers who only wanted access to our transit provider, with customers who only wanted access to our European peers and not anybody else, with customers who didn't want access through UUNet Global, and so on. So we had to try and handle this somehow. With the prefix filters, it was pretty nightmarish to try and do. With communities, it became so simple. It was almost overnight, although it took a while to transition, but it became so simple to handle it using communities. What we did, or as an example, all the customers who wanted access to the exchange point, we just stuffed them into community 100:2100. Okay, remember the internet format for using communities. The first number in front of the colon is your own autonomous system number, and the second number is just, well, some number you want. Doesn't matter, you make it up. So customers who wanted access to all your exchange point peers, we put them in community 100:2100. Customers who want access to the private peer, we put them in community 100:2200. So the customer who bought local connectivity, he was in one community. Customer who buys peer connectivity is in 100:2200. Customer who wants both goes into both communities. Customer who wants the internet got nothing set at all. Okay? And then the way we give the customer the connectivity is, well, if we want to announce them to the exchange, we set up a policy on the peering with the exchange that says we only send community 100:2100 to the exchange. So all the prefixes belonging to that community get sent to the exchange point, and so forth. So you have one very, very simple filter. The router checks the prefix, the community membership of that prefix. If it belongs to 100:2100, it goes out to the internet exchange point. If it doesn't get sent there. Okay. Right, so the communities are set on the aggregation router, where the customer actually connects to your network. So you set all the communities there, where the prefix will go into the IBGP. And then the community is carried as a BGP attribute through the IBGP to the border router or wherever, it's almost disappeared, the border router on your network. Okay? There's a huge advantage of trying to do this. You don't need to change any filters. If you've got a new customer and you're using prefix filters, what do you have to do? Well, if a customer bought exchange point and exchange point peering only, you'd have to go to the exchange point filter list and add in his prefix, add in his address block. And then you've got to do a soft reset of the BGP peering to send that address block out. Or in the old days, before soft reset on BGP, you had to do a hard reset, which you could only do at the maintenance time. So in my case, it was setting an alarm clock at 4 o'clock in the morning, going through to my office and logging in and doing a reset of BGP so the new prefix filter would take. Okay? So community makes it very, very easy. When your customer installation engineers add the new customer, the community is automatically set and they get automatically announced immediately. Okay? Makes it very, very easy to do. So you, the BGP guru of your network, doesn't have to go and do fairly basic maintenance work like this. It can be left to the customer installation folks. Okay? So that's a very, very simple example. And ooh, the wireless is gone. So that is a simple example. Now, as I say, more experienced operators tend to have more sophisticated options available. But you find that ISPs don't sit down and try and come up with some really complicated policy. They generally build on things by having a requirement like this. Customers have got particular needs. So they just create that community that handles the job. And then maybe a few months later, they've got another service they want to sell or another feature, so they create the community that handles that. You can add to them quite simply. Okay? My advice is always start with a nice, easy example and then proceed onwards as you gain experience. Now, ISPs also create communities to give customers bigger routing policy control. Customers who multi-home between you and other providers want to do stuff. Or maybe customers who connect to your backbone have strange requirements to get access to different parts of your network or your transit provider networks. And rather than you sitting on the phone 24 hours a day with them, manipulating BGP until they're happy, because, well, you have to try and keep customers happy, they will set up communities to try and let the customers do this themselves. So these are what I would probably more call public policy. And, the communities are listed publicly, probably for the customers to actually use as they wish. I find these are listed in the Internet Routing Registry, or they can be listed on the ISP's website, or so forth. So I've got some examples which are I've just pulled off the internet to show you. And these communities are here really to try and reduce the technical support burden. You don't want your customers phoning you up all the time saying, "Oh, I need to change my multi-homing. I've got too much traffic going this way. We want some more to go to you. Can you do this? Can you do that?" Okay, that all takes time. Especially your customer support people. Do you want them interfering with your eBGP sessions to other ISPs? You generally don't want them to do that. It's all fairly fine-tuned stuff. You don't want somebody coming in if they don't know what's going on. Okay, so it reduces the technical support burden, but more importantly, it reduces the amount of router reconfiguration. I mean, if you switch a router on and leave it alone, it'll work quite happily. But the more you tend to log into it, the more you tend to change the configuration, the more it's likely to break. It's just one of those things. And the greater chances of mistakes are happening. So here's the first example. You probably can't see it at the back of the room. I'm sorry about that. Here's SprintLink's example. That's on their website, sprintlink.net/policy/bgp.html. They list communities that their customers can use. So for example, the first group is 65,000:X, which means do not advertise to ASX, where X is any of their particular peers. So they actually list the ASs that are supported at the top there. So that's probably the major peering ASs. And then they've got like 65,001:X, and that one says insert a AS1239 prepend in the announcement of this path or this prefix to ASX, and so forth. Okay, so they can do AS path prepend. So you send that particular community to Sprint, they will do the AS path prepend towards the peer you specify. The next one, 65070:X, do not advertise, and so forth. And so forth. They've got quite a long list of communities, what you can send to them, and they will do things with your particular prefix. So that lets you manipulate your load sharing or your multi-homing with them. Okay, so that's the first example with Sprint. So you can go to the website and pick that up. MCI in Europe, they've got another one. That permits customers to send communities which determine local preference within MCI's network, or the reachability of the prefix, or how the prefix is announced outside of MCI's network. And I've taken this one from the RIPE routing registry. So you do a whois on whois.ripe.net on AS702, and you find this buried away down at the bottom of the AS object. Okay, so we've got 702:80. If you send them 702:80 community with the prefix you're announcing to them, they'll set local preference to 80 with an AS702. Okay, so they'll make it a lower local preference. So it'll be a less preferred path if you're multi-home between them and somewhere else. Or you can send them 702:120, which will set local preference to 120, make it higher than the default. 702:20 only announced to MCI's autonomous systems and their customers. Well, that's very similar to the one that I mentioned before about announcing to exchange point or to private peers. It's the same idea. 702:30, keep within Europe, don't announce to other MCI autonomous systems. Then you see 702:1:2:3. It'll do the prepend of 702 once, twice, or three times in any announcements to any of 702's peers. So you don't do the AS path prepend between you and 702, you get them to do the prepend to their peers. So it means that traffic between you and them stays on that primary path, but any other traffic to anywhere else on the internet will go over your alternative path. So it's really helpful for multi-homing. And they've got a lot more. I haven't put them all in here, but you get the general idea of what they actually support. Actually, the web URL there gives the complete list. British Telecom's network, if you do a whois on AS5400 on whois.ripe.net. Well, this is one of the biggest community lists I've actually seen. I mean, this one's been around for a few years. This is quite a nice list. Again, if you're thinking about using communities to support your own network operation, have a look at this particular list that BT Ignite have for their network. For example, if you send them 5400:1000, it means do not announce this prefix to all peers and transits. If you send them 5400:2000, it means we do a single prepend of 5400 on the announcement to all peers and transits. If we send them 5400:1504, it means do not announce to AT&T. Or if we send them 5400:2504, it means send to AT&T with a single prepend of 5400. I actually work with an ISP who's a customer of BT Ignite, and I've played around with these communities quite a bit, and it's quite interesting to see them in action, and they actually are quite useful, I find. Okay, it's a huge list. It would take up several slides to even try and do it here, but have a look in the AS object for the full list. And as I say, it seems to be used by more than just BT. It's this concept of the list is used by quite a few ISPs. So in the final, gosh, not very much time, the final 3/4 of an hour, deploying BGP in an ISP network. So this is some of the operational deployment thing that I want to try and cover for you. So how do we use it on our network? Well, these are the 4 subjects that I'm going to cover. The first one, the role of IGPs and IBGP. They are different things, even though sometimes I've people telling me that, well, you know, you can use IBGP to do what an IGP does. Going to cover aggregation. Aggregation's pretty important, so I'll cover that one in reasonable depth. How we go about receiving prefixes in our network, because again, that's a lot more complicated than it should appear. And then we'll finish off just with some configuration tips and some things to think about. So, the role of IGP and IBGP. Well, IGP is an internal routing protocol. 2 commonly used examples of those are ISIS and OSPF. They're used for carrying infrastructure addresses. Now, infrastructure means your network. It's your physical network, so your routers, how they connect to each other. That's an infrastructure address. The point-to-point links or the LANs or whatever that these routers sit on are the infrastructure. They're not used for carrying internet prefixes. You still see the odd question every now and then from people saying, ooh, I want to distribute all my BGP into OSPF to do X. You don't do that. Well, you certainly don't do it in the internet. You can try and put 160,000 prefixes in OSPF if you want to, but your router probably won't function too well. Customer prefixes don't go into your infrastructure routing protocol either. Okay? Customer prefixes, well, your customers want to reach the internet. The routing protocol that's used for reaching the internet is called BGP. So you put your customer prefixes into internal BGP, so that internal BGP can pass them to external BGP. I mean, I suppose it all sounds really quite simple, but as I say, you'll be surprised how many people get completely tied up in knots with the difference between OSPF and ISIs and using BGP. Okay, the IGPs are simply there to let your infrastructure talk to itself. So the design goal that I always try and set people up with target for is to minimize the number of prefixes in the interior routing protocol. The fewer prefixes, the better it will scale, the faster it will converge. BGP can be used internally as IBGP and externally as EBGP. IBGP is used to carry some or all of the internet prefixes across your backbone, and it can be used to carry customer prefixes. Right, so that's where your customers connect to your network, and you put them into IBGP. EBGP is used to exchange prefixes with other autonomous systems, and is used to implement routing policy. Okay? May I sometimes try and point out that IBGP and EBGP are different. EBGP is used to communicate routing information between your network and another network, whereas internal BGP is to provide connectivity with your network and outside networks or the rest of the internet. The model is a bit like this. Each bin, I suppose, is a different autonomous system. Within the autonomous system bin, you have an IGP that lets each device in the autonomous system speak to every other device. You've got IBGP that provides the transport across that network. And EBGP is basically the scoop that takes things from one IBGP and dumps them into another IBGP. And that's pretty much how the model works. And this model has been around since, well, probably, I don't know, I've been using this ever since I've been in the industry, but in common use probably since 95, 96. This is generally how it's set up. The only reason I make a big point about it is that a lot of people are still trying to do it other ways. And given that this way has worked so well for so long, I don't really see much point trying to do something that's actually harder to achieve. So, some things: do not try and distribute BGP prefixes into an IGP. People still try and do this. You try and redistribute BGP into OSPF. I see a question every now and then on the different mailing lists asking about trying to do this. Maybe if you're supplying MPLS VPNs to a customer and using BGP to transport customer IGP, that's fair enough. That's a different issue. But within an ISP network, taking 160,000 prefixes that are in the internet routing table today and putting them to ISIS and OSPF is not a guarantee to a happy network. Try not to distribute IGP routes into BGP. IGP is a rapidly changing routing protocol. BGP doesn't take too kindly to getting lots of updates being pushed into it all the time. And try not to use an IGP to carry customer prefixes. If you have a small network with maybe 10 customers, that'll work fine. When you've got 10,000 customers and carrying each prefix in the routing table, it's probably not going to work too well. I was doing these slides many, many years ago for the first time, and somebody was sitting beside me watching me, and he sort of went chortled, ha-ha, when he saw me writing all this, because he said, oh, well, but in my network I've got 15,000 prefixes running in my OSPF, and it's working just fine. It was about 3 months later I got an email saying, well, we need to try and talk about this stuff that you were writing in your slide, because his routers were starting to fall over. More from the lack of, or the difficulty of the network actually converging. A link would break on the backbone. OSPF was taking about 5 minutes to converge on the backup path because it had to work through 15,000 prefixes to find the next best paths. So it's the basic thing is the network will not scale if you try and do any of these things. Keep the separation, keep IGP for the routers to talk to each other, keep IBGP to carry all your prefixes around your backbone, and it will work just fine. Putting prefixes into IBGP. Well, use IBGP to carry the customer prefixes. Don't ever use IGP. Point a static route to the customer interface. Put the network into the BGP process like that. Ensure that implementation options are used so that the prefix always remains in IBGP, regardless of the state of the interface. So some implementations, for example, in the Cisco one, if you point a static route at an interface, the interface goes down, the static route basically drops out of the routing table. You can put on permanent keyword, which will make sure that the static route is always there. Doing that will ensure that your IBGP doesn't flap every time a leased line to your customer goes up or down. Now, aggregation. Aggregation basically means announcing the address space that you get from the regional registry to the other autonomous systems connected to your network. I mean, it's such a simple concept, but this is the one that seems to be causing huge amounts of issues. And I don't know, I suppose that all over the years, I've never really thought anything of aggregation at all, but I don't know, people just seem to have big problems with the concept. It's like you get an address block from the registry, whether it's a /19, /20 or whatever. That's what you get. Surely that's what you announce to the internet. But a lot of people still see it as, ooh, Aaron have given me 16 Class Cs. I was like, well, what's a Class C? Class C was phased out in 1994. Aaron didn't even exist in 1994, so they definitely couldn't have given you any. And even if they did, they don't exist either. But that's part of the issue. People see lots of /24s. They can think in Class C units, and that's how they work. And it's not just that. Other ISPs get bigger address blocks. I've seen ISPs get /12s and /10s and so forth, and they announce them all as Class Bs, /16s. And, well, if you get an address block from the registry, sure, you can just announce it as an address block. I guess the issue is that people get mixed up between what you announce to the internet and what you use inside. That's partly why I kind of say, well, eBGP is different from iBGP. What you announce to the internet by eBGP should be aggregate. What you use inside your network with an iBGP, well, that doesn't matter. iBGP can carry hundreds of thousands of prefixes. Okay, so each customer that connects to you gets a /whatever of address space. You put that into iBGP, but just inside your own network. At the edge of the network, you only let out your aggregates. You can create sub-prefixes of the aggregate to aid with multi-homing. But quite often, when I do the multi-homing tutorial, as I say there, people's idea of multi-homing is, okay, if I just chop this into 24s and just spray it out into the internet, something will happen. And yeah, I mean, something will happen. Something always does happen. But it's never optimum. So the only time that sub-prefixes are created, or yes, for running within your iBGP, or to aid with multi-homing. Okay, so the address block should be announced to the internet as an aggregate. Sub-prefixes should not be announced to the internet unless there's special circumstances. So more later means, well, check out the multi-homing tutorial and you'll see some of the examples of what I mean there. Aggregate should be generated internally, not on the network borders. That one's pretty important as well. Maybe not so for folks here in North America, but ISPs who've got networks in different continents and so forth, that's actually quite important. I mean, one of the mistakes that we made while sitting in the UK, we had 2 points of presence in the US. And we lost the cable going across the Atlantic once, and we generated the aggregate in the US. Of course, with the cable breaking, our router in the US didn't actually know that the cable had, didn't know the cable had broken and still happily carried on generating aggregate. There's no command that says if cable breaks, stop generating aggregate. So our router was quite happily generating the aggregate here in the US. Well, our backup path was working just fine, but of course the best path was back to aggregate in the US, and our network got blackholed. So that was one lesson learned. We had to phone somebody up. I think it was on the 4th of July, actually, which was the worst possible day to phone somebody up to actually get them to switch the router off, because we couldn't get access to it. So generate the aggregate in the core routers. I mean, I talked about route reflectors earlier on. The best place generally is all natural route reflectors or any of the core routers in the backbone, not anywhere at the edge of the network. Then if the edge of the network gets chopped off, you don't leave yourself with a black hole network. Now, ISPs who don't and won't aggregate are held in poor regard by the community. I don't know, each time I say this, I'm beginning to wonder more and more if it's wishful thinking rather than reality. 10 years ago, I think this was reality. I mean, the CIDR report was there and people were determined not to be in the top 30. Nowadays, I've seen people do marketing based on the fact that they appear in the top 30. Because they say, we're the biggest ISP because we appear in the CIDR report. But anyway, I still wish and hope that people think that ISPs who don't aggregate are held in poor regard by the community. Registries publish the minimum allocation size, so it tends to be from /20 through to /22. And also the sizes are different for different address blocks. Okay? You can't just say, oh, well, Aaron's minimum allocation today is /21, therefore it's /21 for the entire Aaron address space. It's not. If you go to the website, you'll find the minimum allocations and assignments I've made out of each block. So going on that, there's no real reason to see anything longer than a /22 prefix in the internet. But, well, surprise, surprise, there are 87,000 /24s. Okay? I was saying something about people thinking of class Cs, wasn't I? It's a bit more than a theory. See, here's an aggregation example. Okay, your AS100 has got a /19 address block, 100.10/19. The good ISP, they announce it to the internet. The customer's got a 100.10/23. They announce it to AS100. Okay, life is good, all is happy here. Customer link goes down, so the /23 network is unreachable. /23 is withdrawn from AS100's IBGP, because the least line to the customer goes down, so the static route goes away, so the IBGP entry goes away. But of course the ISP is still announcing his /19. No BGP hold down problems, just nothing. As far as the world's concerned, the customer is still there. And if you do a trace to the customer, it stops an aggregation router that should have been originating the prefix or somewhere. Customer link returns. He may have come back next day after switching his router off before going home, or it could have been a circuit failure. So the /23 network is visible again. It's re-injected into the AS100's IBGP. The whole internet becomes visible immediately. Okay, so the customer starts up his web browser, he's switched on his router, and he can browse the whole internet, and he's happy. So the customer thinks, wow, good service, let's switch my router on, everything works, as it should. What about this case? This is an all too common case of an ISP who just leaks his IBGP to the entire internet. He doesn't do any aggregation whatsoever. Customer again gets that /23. Customer link goes down. /23 is withdrawn from the AS100's IBGP. Of course, the ISP doesn't aggregate, so the /23 network withdrawal is sent to all the peers, and it ripples all the way through the internet. Flat damping couldn't happen. AS path amplification, whatever. That can all happen, goes bad. Customer link returns, the 23 network is now visible, re-advertised to the peers, advertise all the way through the internet, load on the internet backbone router. It can take maybe 10 to 20 minutes to get across the entire network. And of course the customer is expecting, when he switches his router on, he's expecting everything to work immediately. And after 10 minutes he gets fed up and phones up and starts complaining about how bad the service is. And the ISP doesn't know what to say because, as far as he's concerned, everything's there and it's just working. So he does the usual thing and says, oh, well, the internet's broken, it usually happens. Pretty unreliable thing. Okay, so there's the difference. There's no need for this ISP to be announcing all this detailed address space to the internet. The impact is bad quality of service for the customer. So, summary of that, good examples what everybody should be doing, because it adds to the internet stability. You don't have all the routers and the internet figuring out the best path options as this prefix is withdrawn. Because the prefix will be withdrawn, but withdraw at different rates, different BGP implementations have different expiry rates and so forth. So you get this kind of cascading withdrawal through the internet that all causes problems. You don't have the flat damping and so forth. Reduces the size of the internet routing table, reduces the routing churn, it will improve convergence, makes quality of service better for everybody. So what's going wrong? Well, internet today, this was a few days ago, 162,000 prefixes. This is my view. Before anybody jumps up and says, oh, but this is not the internet routing table, there's no such thing. I know there isn't such a thing. This is my view. This is on APNIC's router in Japan, just to pick somewhere different. One of the things I do in my routing report, which I send to NANOG every week, is just have a look at the routing table and have a look at some of the regional prefixes and some of the aggregation that's possible and so forth. And one thing I do is figure out the maximum aggregation possibility. And I find that if I apply maximum possible aggregation to the Internet Routing Table, in other words, aggregate, as ISPs should be doing, it will come down to 94,157 prefixes. So, what's that? That's about 68,000 prefixes caused by, I don't know, laziness, junk. Even further, the number of unique prefixes in the Internet is 78,129. So that's places where ISPs have announced an aggregate and have announced more specifics in that aggregate as well. I've dumped the more specifics. Prefixes which are smaller than the registry minimum allocation sizes. I've programmed in the minimum allocation sizes for all the registry blocks, and there's 75,000 prefixes that are smaller than that actual size. /24s, 88,000 /24s. People always blame the former Class C space. Well, it's all those Class Cs that were handed out in the 80s. No way. 5,700. That number's been pretty steady over the last few years. And just out of interest, number of ASSUs, 19,500. So this is what's given rise to the new swamp, I've called it. Swamp space is a name that was used for areas of poor aggregation. This was back in the 90s again. That was swamp space. The original swamp was, well, network 192/8, the original Class C, well, the original first /8 of the Class C block. That name came about just after the deployment of CIDR in '94. But the new swamp is creeping across all parts of the Internet, not just the registry space, but also the legacy address space as well. So, before you start thinking this is a rant about aggregation, well, I suppose it is a little bit of a rant about aggregation. So I started doing my report way back, it was March '99, so I took a snapshot, May '99, so this is, 6 years ago. Registry blocks contributed almost 51,000 prefixes to the Internet Routing Table. So that's about 86% of it. So apart from network 214 and 215, which are separate allocation, the rest of these blocks that I've put up here are the registry address blocks. So they hadn't started using any of the former Class A space apart from network 62 and 63. We're still working through the former Class C address block. So moving on to 2005, so we probably can see some notables here. Network 202 and 203/8 have gone up to like 8,500 prefixes each, gone from like 2,500 or 3,500 in '99. So there's been pretty substantial deaggregation of those particular address blocks. And I mean, those ones, the registry actually had completed all allocations, so there were no new allocations being made out of there. So there's been a fairly substantial deaggregation going on. And even 214 and 215, I mean, those were assigned back then, and there were two and four announcements respectively. The owner of that one has decided to deaggregate just for fun as well. Okay, so 316 and 356. One thing that's nothing to do with this tutorial whatsoever, network 87 and 88, I believe those are allocated to the RIPE NCC now. Why you see two there is because they're making an announcement of two addresses out of that address block so that people who are filtering the former A space can actually check the filters to see if those prefixes come in. It seems to be like a weekly topic on the NANOG mailing list, like, ooh, such and such has still got filters and I can't get to. So the registries, well, certainly RIPE NCC have started doing something like that, which is why you see two there. What else on this one? Network 24 is used by a lot of cable providers, and that one's significantly deaggregated as well. Network 66, if you see that one, 5,953 prefixes. What else? 209/8, 5,000. 216/8, 6,200, and so forth. So there's reasonable amount of deaggregation going on within each /8 block. Notice the number's still about the same, 88% of the Internet Routing tables caused by the regional registry address blocks. Okay, so registry space shows creeping deaggregation. Seems that a RIR/8 block averages around 4,000 prefixes once fully allocated. So once the registry has used up the /8, it seems to average around about 4,000. I think I'm being generous there, because I wrote that and I looked at it the other day and I thought, it's more like 6,000 or 7,000. So the existing 58/8s, assuming the same thing happens, that's going to cause 232,000 prefixes in the Internet Routing Table. Okay? Today we're 160,000, so probably about this time next year we'll be about 232,000. So some food for thought. There are 74/8s left. Okay, that's entire V4 space. It's going to run out any time in the next 4 to 20 years, depending who you listen to. Doesn't matter, I don't care about that, but if we have that sort of density for the remaining /8s, then we're going to end up with probably 500,000 prefixes in the Internet Routing Table. Plus, of course, another 10% due to the registry, non-IRR space deaggregation. So probably say 600,000 prefixes. That's being extremely generous. I think it's going to go more like double that. So we could well have over 1 million prefixes in the V4 routing table by the time it runs out, whenever that is, at a guess. Okay, what are the main reasons for this? Well, whenever I ask people, or people give me feedback, they just say, oh, it's traffic engineering. BGP traffic engineering, people are multi-homing, that's causing it all. Well, I've had a look at it, and I can't find very much evidence for that. And I've pretty good suspicion the real reasons are lack of knowledge, laziness, and in some cases, deliberate and knowing actions. People are deliberately deaggregating. Why do I say this? Well, Jeff Houston's done a lot of work in the BGP table, and his website, putaroo.net. If you look at bgp.putaroo.net, he's got pretty much every single BGP statistic you could ever hope for. 157,000 total announcements when I did this. His view is from Reach's network, so slightly different view from mine. After aggregating, including full AS path information. Okay, so this is the just aggregating, so it's including everybody's traffic engineering and so forth. 108,000 prefixes. So that's just taking the routing table as it is, and just you check the entire AS path, make sure it's a duplicate AS path, and then join all the aggregates, join all the prefixes together to make an aggregate. If you did that, you'd reduce the Internet Routing Table to 108,000 prefix. That's a 33% saving. If you now aggregate by origin AS, in other words, ignoring the traffic engineering, so you just look at the origin AS, who's originating the prefix, then aggregate, you only pull it down to 93,000 prefixes. That's only a 10% saving. So those people who say, well, all the deaggregation is caused by traffic engineering. Nah, it's only 10% is caused by traffic engineering. 33% is caused by the Class C fan club. Okay? Just by the laziness or whatever else. It's not caused by, engineering or operational requirements. It's caused purely by laziness. Okay, so traffic engineering causes 10%. The Internet Routing Table, deliberate deaggregation causes 33%. Now, efforts to improve. Well, that does the deliberate deaggregation by lack of knowledge or deliberate or otherwise. Well, if you go for the lack of knowledge bits, people then say, oh, well, but I don't know what's available. It's too hard to configure on my router. And like, well, okay, you can explain all the configuration commands, and then you discover it's not that hard whatsoever, so they need to find another excuse. Oh, well, there are no tools available. I don't know what I'm announcing. Well, it's very easy to find out what you're announcing. The CIDR report has been around for years, and as I said earlier, it seemed people always try to keep off the top 30. Now I've seen people do positive marketing on the fact that they are in the top 30 because they're the biggest or whatever. Tony Bates started that, probably around about 95 he started it. I took it over and combined it with Jeff Houston's work. So Jeff pretty much looks after the CIDR report now. It's got its own website. Results are emailed on a weekly basis. Most operations lists in the world get to see it. So people who are not on the operations list probably won't know about it. But then which operator isn't on an operations list? It also computes the size of the routing table, assuming ISPs performed optimal aggregation. Well, I showed you a sample of that. But the best thing is the website lets you do searches and computations of aggregation based on your AS. You can put your own AS number in there and find out what Jeff's views, and he's got a considerable amount of views feeding this, what his views actually see. So you can figure out whether you can aggregate or not. So when people tell me, oh, well, I don't know what I'm announcing, I ask them for the AS number, pop it into the CIDR report, and up it comes. And if there's no AS path differential in any of the announcements, then it's like, well, why aren't you aggregating these? Tell me your router configurations. And sure enough, they're just leaking the IBGP out into the EBGP. Okay. So for those of you who haven't seen it before, this is what the home page looks like. I've just scrolled a little bit down. And the home page actually is, if I can find it, it's probably more something like that, and then so forth, so on it goes. Okay. But the website's there for the CIDR report. And there are various links here, so you can click on plot BGP table size and get your own graph and so forth. Okay, so the number of prefixes in the routing table, the size after aggregation, we'll plot the growth there. The number of ASs in the routing system, he sees less than I see, which I find quite interesting, and so forth, and the various things you can do. Aggregation summary, so here are the top, I think that's the top 20. Top 20 what? I don't know. Oh, top 20, who could do better, I suppose. So the net gain is how many prefixes could be lost from the internet routing table if the ISPs concerned could aggregate a little bit. I think the number 2 ISP there is the one that could do a lot better. So you can see some really obvious ones, announcing 805. If they did aggregation, they could announce 8. Further down, 264. If they did aggregation, they could announce 6, and so on. But they're the savings that can be made. So that's quite prominent in the CIDR report. They can actually be listed in there. Okay, so what else? Top 20 added routes this week per originating AS. So in this case, Comcast have added 154 prefixes. Top withdrawals, Lighthouse Communications have withdrawn 45, and so forth. So it tracks those sort of changes on a weekly basis. What else? Those are announcing more specifics. These are more specific than the original class-based prefix mask, or more specific than the registry allocation size. So Jeff's taken roughly what I've done, but he's also included the class-based mask as well. So again, well, the top announcement of 1,103 more specifics out of a total of 1,467 announcements, and so forth. And it goes on and it goes on. So here's one I've put AS1239, Sprint Link's autonomous system, into the CIDR report website to find out what the aggregation is going on here. And this is the sort of output it can give you. So they're announcing 24.221.00/18 and 2/19s within that. So what this says, you can withdraw those 3 and you can announce 224.221.00/17 with no loss of routing information. Likewise, 224.221.128/19 and 160/19 could be withdrawn, and you announce 224.221.128.0/18 with no loss of information. Okay, and so on it goes. For fun, I put an AS701, and that produced pages and pages, but here's a sort of example again you can do. It takes all the prefixes originated by 701 and show you the aggregation possibilities. For example, they're announcing all those /12s out of network 63, but that all could be withdrawn in this view and announce a 63/9 instead. Okay? And there's just another graph just to back up what I was saying before. Routing table as it is right at the top. If you aggregate by AS path, it would pull it down to about the 108 or so thousand prefixes I said. Aggregate by origin AS, it comes down to about 90,000-ish. Okay, and you can do more severe aggregation if you wanted to. So aggregation on the internet could be much better, which is why I've been harping on about it for the last few slides. 35% saving is completely feasible. If every ISP just aggregated, didn't leak the iBGP out to the internet, then we could reduce the routing table by 35% quite easily. Tools are available. The commands in the router are really easy. If anybody doesn't know the Cisco command, I'll tell you. But any implementation has a facility for generating an announcement to the internet. Every implementation of BGP can filter prefixes. So you set up the filters to only announce your aggregate to the internet and don't announce your internal specifics. The CIDR report webpage will help you in any of this. It's very, very easy. Put your AS number in, pick the view that you want to use, and it will give you the answers. So that was announcing prefixes. The receiving prefixes. Well, there are three scenarios for receiving prefixes from other autonomous systems. It's a customer talking to BGP, or a peer talking BGP, or an upstream or transit talking BGP, and each one has got different requirements. For starters, if you're talking BGP with your customers, ISP should only really accept prefixes which have been assigned or allocated to the downstream customer. If you know what your customer is going to announce to the internet, that's what you should be accepting from them. So you can set up quite a specific filter to do that. If the ISP is assigned address space to its customer, then the customer is entitled to announce this back. If the ISP is not assigned address space, then, well, find out from your customer what they are entitled to assign, to announce. Okay, for example, you look up in the WHOIS database of the registries, who actually owns or has the use of that particular address block. Okay, so there's one example. I've just picked on APNIX network 202.12.29.0. I've looked up in their database and it says, yep, that's APNIX address block, it's assigned address space, and it's portable address space. Okay, it means it's an assignment to the customer, so the customer can announce it to you. Here's another example. This one's assigned but provider aggregatable. In other words, it's part of the provider aggregate. So if you weren't, well, this is quite an old one. If you weren't UUNet and this person came along to you and said, I want to announce this address space, well, you'd have to actually check and see if they could. Like they were still customers of UUNet and they weren't, then this isn't their address block. A peer is an ISP with whom you agree to exchange prefixes you originate into the internet routing table. Okay, so prefixes you accept from a peer are only those they have indicated they will announce. Prefixes you announce to your peer are only those you've indicated you will announce. Okay, so there's this, you give a list of prefixes you're going to send to them, and they will give you a list of prefixes they will send to you, and you configure your routers to accept those prefixes. Okay, agreeing how you will do it, well, people rely on email, so email documentation is quite common for exchanging prefixes as part of the peering agreement, and then ongoing updates. Okay, and then you just manually configure your router filters. A lot of people don't like configuring router filters by hand, so they'll use something like the Internet Routing Registry to do that. And the configuration tools like the IRR toolset, which is looked after by ISC these days. And that will produce router configurations based on what's in the Internet Routing Registry. So those are the two ways that people will try and notify each other of the prefixes they intend to announce. Some ISPs will use the Internet Routing Registry, or they will use their own routing registry. Other ISPs are quite happy to do the email exchange and the manual updates. Now, your upstream or transit provider is an ISP who you pay to give you transit to the whole internet. Receiving prefixes from them is not desirable unless it's really necessary. Okay, again, it's the usual thing of, do you want to get the full internet routing table from your upstream, or do you want to get just the default route? Default route is just as good. It says the same thing. It says your upstream knows how to get to the whole internet. If you want to get the full internet routing table, that doesn't mean you just take everything. You've got to be careful. You don't want to accept private address space, for example, because that should not appear on the internet. Basically, I've written RFC 1918, which is private space, and there are other prefixes as well which have got special use, like 169.254, 127/8, and so forth. RFC 3330 lists a lot of these special use prefixes. Some of them should be routed, but most of them should not. Don't accept your own prefixes. That should be reasonably obvious. You don't want to hear your own prefixes coming from somewhere else. Don't accept the default route unless you need it. Yes, from time to time, somebody likes injecting the default route into the internet routing table, so it's probably not a good idea to accept that one, unless you expect to get it from your upstream. And then the other one there, I've got don't accept prefixes longer than a /24. That's historical. Some people do that, other people don't. The best place to go actually is to check Project Cymru's list of bogons. Okay, the bogon list is there. At that URL, the documents/bogonlist.html. Big word of warning, if you're going to use this bogon list, you must keep it up to date. I can't overemphasize must. It's must, must, must. You have to do it. It's not a case of just copying the list off the URL and then dumping it in your router and fitting it and forgetting it. You have to keep it up to date. Rob Thomas sends nagging emails however often to virtually every mailing list he can think of saying, I've updated it, please update your filters. But every day I come across people who can't get connectivity somewhere because somebody is running a really, really old bogon list. So if you're going to use this bogon list, keep it absolutely up to date. For example, when a new registry gets a new address block, the bogon list will be updated. Registry gets a new address block, they're going to announce specifics out of that block. Those specifics are going to be used by ISPs who need reachability in various parts of the internet. So if major ISPs are filtering it, then they're not going to get the connectivity. So keep it up to date. Now, receiving prefixes means really paying attention to prefixes received from customers, peers, and transit providers. That ensures you've got integrity of the local network. You don't want to accept any old rubbish. Okay? It's also the integrity of the internet as well. You don't just announce something that somebody comes along with just because, oh, well, you know, they pay you money, so you're not going to ask any questions. I mean, you can probably run it like that if you want, but don't expect your peers to be too friendly if you start announcing their address space, for example. Now, just in the last few minutes, just some configuration tips and hints. So just some reminders. The first thing, IBGP is generally set up in routers between loopback interfaces. It's quite rare to build an IBGP running between physical interfaces in the router. I didn't go over IBGP design in the first part of the presentation, but IBGP is built between loopbacks on the router rather than between physical interfaces. If it runs between physical interfaces, the physical interface goes down, the IBGP session goes down, whereas you want to build a stable IBGP for your backbone. So run the IBGP between loopback, not between real interfaces. Make sure the IGP carries the loopback/32 address. Okay, that way you've got your valid next hop and so forth. Consider the demarcation zone networks. Some people use unnumbered interfaces, so they don't have an IP address in the interface, they use an unnumbered version. Or other people, rather than carrying all the point-to-point links for customer connections, they will use next hop self on the IBGP neighbors. So we introduce a customer network into your IBGP. The next hop is not the point-to-point link going to the customer. The next hop is actually the router that it connects to. Okay? So again, you can keep the IGP small. You don't need to carry these /30s around. Some ISPs put the /30 in the actual IBGP. It's fine doing that, but make sure you don't leak your IBGP out to the internet. But whatever you do, try and keep the demarcation networks out of the IGP. I generally say what should be in the IGP is what you need to run your internal routing protocol. So the point-to-point links between the routers and the loopbacks is generally it. So next hop self, it's used by many ISPs on the edge routers. I would say it's preferable to carry the demarcation /30 anywhere, even in IBGP. But some people needed an IBGP for link monitoring and so forth. But it reduces the size of the IGP to basically just the core infrastructure. Some ISPs, as I said, use IP unnumbered interfaces. Other people don't particularly like it because they find it harder to troubleshoot. BGP speaker using the next hop self will then announce the external network using the local address, which is the loopback address, as the next hop, rather than the point-to-point link address. So it means you don't need to carry that around. The next thing, templates. Can't sing the praises of templates high enough. It's really good practice to configure templates for everything. A custom configuration is one that's pretty hard to maintain, because if you've got custom configuration for one router, you're going to custom configure every router on your network. It's actually a lot better to come up with a configuration template. So whether it's a standard router template, or whether it's a security template, or BGP template, and so forth, it's a good idea to have that. If you need to make a change in your network, you change the template, and then you reapply the template to the whole backbone. Other thing is, vendor defaults tend not to be optimal or even very useful for ISPs. Okay? You want to set up the defaults for your network, not what somebody who's put the router together has said. Okay, so a lot of ISPs create their own defaults by using the configuration templates. Again, the Project Cymru website has got some BGP templates. They've also got security templates, which are considered best practice for several implementations. So have a look at those. So I've got some highlights here just for example. You run the iBGP between the loopbacks so that the IGP can do intelligent reroute. Don't run it between the physical interfaces. Use next hop self, keep a demarcation and external point-to-point links out of the IGP. Always send community with an iBGP. If you don't do that, then accidents will happen. If a customer of yours sends your community no export, for example, and you don't carry communities across your backbone, your no export is lost at the edge, aggregation edge of your network, and something will happen which your customer did not intend. So I generally think communities should be carried across an internal BGP by default. Hardwire BGP to version 4. Yes, it is being paranoid, but if any DOS attack is possible, somebody could try and maybe change the version number to 5 or something, who knows. But I've seen people put the BGP version number in there. Using passwords on the iBGP session. I think it's pretty much considered these days as standard practice on putting passwords on all iBGP sessions. For external BGP, well, BGP damping, it should not be an automatic command. Definitely don't use the vendor defaults because they're really too aggressive. Use the RIPE 229 parameters, maybe, if you've thought about it. If you think damping will help in your network, then use it. Otherwise, I would say these days, don't touch. Another one, remove private autonomous system numbers from announcements. Again, most implementations have a facility to strip out private ASs. Private ASs should not appear on the internet, so make sure your template removes those. Use extensive filters. One thing that I always did was I'd back up filters with other filters. So I may have a prefix filter that did something, and then I put an ASPath filter that did roughly the same thing, or at least it could back it up if I broke the prefix filter for any reason. Another thing I find that people make mistakes with is they mix up the policy language with filtering. So try and keep the policy language for applying policy and the filtering language for doing filters. And of course, use a password between you and your eBGP peer. Consider using maximum prefix tracking. I mean, the basic maximum prefix is probably a bit vicious because once you hit the maximum prefix limit, the BGP session is torn down, whereas most people probably don't want that. But you do want to try and be aware of events where if you're expecting 10,000 prefixes from your neighbor and they suddenly send you 160,000 prefixes, you want to find out about something like that. So consider using maximum prefix tracking at least, where the router will notify you if something bad goes wrong. If something bad goes wrong, at least keep the BGP session up, but let the router notify you that something could be amiss so you can go fix things. Logging the changes of neighbor state. Capture those logs and keep a watch of them as well. And more than just on the router, keep a note of the logs on the router as well as on your network operations system monitoring center or service. Okay? Keep a note of the state changes of the neighbor, and then if any unexpected things happen with any peerings, you can be right on there. The final one that people don't think about very much is the administrative distance. Try and keep the administrative distance for BGP higher than that of any interior routing protocol. You don't want prefixes that are in BGP as well as your interior protocol to be around, because you don't want BGP to override your OSPF or your ISIS. And I've seen things like that happen before. For example, in Cisco iOS, eBGP distance is 20, OSPF is 105. Prefix coming in by eBGP would then override the identical prefix if it was known in OSPF, which you don't want. So generally make the admin distance of BGP higher than anything by OSPF, and you save any accidents from any collisions like that. Some BGP implementations have problems with long AS paths. It can give memory corruption or memory fragmentation. Some people use AS path prepends for fun. Think, oh, well, let's do a 50 times AS path prepend to try and make this path really unimportant. Even though when you explain to them, if it's the only announcement on the internet, you can prepend as much as you like, it's still going to be the preferred path. So I find that some ISPs are limiting the maximum AS path length that they'll accept. I mean, my routing table analysis, I generally see 16 to 20 ASNs being the largest AS path. It's about 23 at the moment, but generally about 16 to 20. More interestingly, the internet's only about 5 ASs deep. It's not getting any deeper, it's just getting thicker. Okay? So seeing a 40 or 50 times, well, 50 AS long AS path is, well, unusual, I would say. So ISPs say, well, we're not going to see anything much longer than 25 or 30, so we're just putting a limit there, and if anything longer than that comes in, we just dump it. Okay? Or, as in this case, this is in the 6-bone IPv6 one. This one was ridiculously long. This was due to an error in one IPv6 implementation. And so it was carrying on announcing this hugely long autonomous system, AS path with that particular network announcement. Another interesting one is RFC 3682. It's called the so-called BGP TTL hack, where you set up your eBGP session where your neighbor sets the TTL to 255. And the local router is then expected to configure to expect the TTL to be 254 for incoming BGP packets. Right, the idea behind this is that nobody anywhere else in the network could send BGP packets with the matching address and so forth and interfere with your eBGP session. See, somebody out here, the attacker, if he sent a BGP packets towards you, will go to router 2, passed on to router 1, but the TTL would be reduced to 253. Okay, there's no way he could send a packet that would reach you with TTL 254. Okay, that's the TTL hack, and it's another I suppose, security feature to consider for eBGP sessions if your router supports it. Okay, again, both neighbors must agree to use the feature. It's generally much easier to perform than MD5. In fact, some people have said that they prefer to use this rather than using a password on the BGP session, because this one only will work between neighboring routers. Provides security, that's why I sort of held up my hands like that. Provides some sort of security for BGP sessions, and of course in addition to packet filters. I would still say that passwords should be used for messages which could slip through the TTL hack. So there could be issues, whether you're in a common shared media, for example at an exchange point or something like that, you probably want to still use MD5. Anyway, the TTL hack is, there was a presentation a few nanogs ago covering that if you want more information. Oh yes, passwords again. Remember, put password on the BGP session. The arriving packets don't have the correct MD5 hash, they are ignored. It helps defeat miscreants. I won't say it's the 100% perfect thing, but you've got to work pretty hard to try and defeat anything like this. As I say, it's a powerful preventative tool, especially combined with filters, proper filters, and the TTL hack. As for communities, I covered communities a little bit earlier on. Really think hard about using communities. I mean, it's, again, say, in my travels, I see a lot of people don't really make much use of communities, don't see how they could apply to their network. And the main advantage is the ease of operation, the ease of actually trying to scale your network and provide proper announcements to different places. Also, if you're multi-homing, you're connecting to different upstreams, check if your upstream support community use. If they do, then you can send communities to them to aid with your multi-homing. Okay, so summary of all that, try and use configuration templates, have a look at the Project Cymru templates for ideas of what are considered best practice these days, or good practice at least. They've got quite a few security and BGP ones, as I said. Try and standardize the router configuration. Don't try and come up with a custom configuration for each box on the network. Be aware of the standard tricks to avoid compromise with the BGP session. I've just mentioned those. Try and find things that make life easier for you. Make your network less prone to errors. Make it more likely to scale. Right? It's all about scaling, really. If your network won't scale, then it won't be successful. That's it, really. Are there any questions at all? If you want the slides, they are here. Should be on the NANOG meeting website by now. Otherwise, they are there, ftpeng.cisco.com/pfs/seminars, and look for the one beginning with NANOG 34. Okay. There are also lots of other presentations, as I said at the start. There are lots of other presentations on that website. So if you want more detail or different things to do with BGP, you're most welcome to help yourself. All right. If no questions, then thank you very much.